Alright, silly people, here's the situation. We have this initial wave function for the harmonic oscillator, and we're going to try to first of all normalize it, and then we're also going to discuss the energy values that we can observe from this state, and then also what the probabilities are for those and what the expectation value for energy is, and some other stuff. During this problem, I will be referring to stuff from uh, problem 10 from this chapter and problem 11 from this chapter. I'll link both of those. Um, 10 mostly because I need the psi 2 stationary state, and 211 because I need a constant from there to simplify the problem a little bit. So let's get right into it. So in the section of chapter 2 where Griffiths talks about the harmonic oscillator, he defines this variable xi, which is just root m omega over h bar times x for brevity, and so I'm going to use that here actually. So in fact, our initial wave function looks like a times 1 minus 2c squared e to the minus c squared over 2. So that's interesting. So to normalize it, we have to integrate the square modulus of this and set it equal to 1. So we have capital A squared integral of 1 minus 2c all to the fourth e to the minus c squared, and that's a really gross looking c dx, and so we need to use this definition of c, which we just did, to get the dx differential in terms of the dc differential, so we can actually do the integral. So there's going to be a factor of root h bar over m omega on everything, as well as the a squared thing. And so I'm also going to start expanding the thing in the parentheses to the fourth. So we've got 1 minus 4c plus 4c squared e to the minus c squared dc. And so we have to expand it again. I just wanted to do it one power at a time, And so that's looking like 1 minus 8c plus 8c squared plus 16c squared minus 32c third plus 16c fourth times our exponential in the dc. So I'm going to split this into multiple integrals in a square bracket. So we got the integral just e to the minus c squared dc minus 8 times the integral c e to the minus c squared dc plus, that's 24, integral c squared e to the minus c squared dc, and then that's minus 32, integral c third e to the minus c squared dc, plus 16, integral c fourth e to the minus c squared. I'm getting really lazy on the c's now. dc and this is evaluated from minus infinity to infinity. Um, I'll tell you that any of these Gaussian integrals that have odd powers of c out front uh, evaluate to 0, so that's 0, that's 0, because they're odd functions. Um, and then I'm going to write a bunch of table integrals for Gaussians that are going to help us evaluate all of these. So first of all, that's the integral of e to the minus u squared du is just root pi, and then that is from minus infinity to infinity. The same integral of u squared e to the minus u squared du is root pi over 2, and then for the u fourth, it's 3 root pi over 4, right? So with those in mind, our little integral that we're doing here is now done, pretty much. We just need to simplify the results. So we have root pi plus 24 root pi over 2 minus 32 times nothing plus 16 times 3 root pi over 4. Right. So that's not terrible. We'll just factor out the pi from everything, put it in the square root outside, and then we'll have 1 plus 12. 16 over 4 is 4 times 3 is also 12. So add those up, you get 25. So you got a equals not the square root of m omega over h bar pi, but m omega over h bar pi to the 4th once we take the square root of both sides, and then 1 over root 25, and then this is what I was talking about when I was referring to problem 2.11. I'm going to collect the term out front. Alpha equals m omega over h bar pi to the 1/4, again for brevity purposes, so we just have alpha over 5 for a, which means we can write the initial wave function as alpha over 5 times 1 minus 2c squared e to the minus c squared over 2. And I'll go ahead and expand that because of what we're about to do next. 4c, oh my god, dude. 4c plus 4c squared e to the minus c squared over 2. So the next thing we're going to do is we need to put this in the form of a superposition of eigenstates for the system. So we're saying that we want it to look like sum over n cn psi n. And so for the harmonic oscillator, you kind of have to do this backwards. And let me actually do this in blue. So the reason that I referred to 210 is because that's the one where we calculated the psi 2 stationary state. And that was, just looking at my result here, 1 over root 2 m omega over pi h bar to the 1/4 times 2m omega over h bar x squared minus 1 times e to the minus m omega over 2h bar x squared. But once we make the substitutions back to the ones for this problem, c and alpha, we just have alpha over root 2 times 2c squared minus 1 e to the minus c squared over 2. And so we're going to solve this for c squared to plug back into the wave function that we're working with. So that is looking like c squared is psi 2 over alpha times root 2 times e to the positive c squared over 2 plus 1, and then divide both things by 2, so 2 here and 2 here. So it's psi 2 over alpha root 2 e to the c squared over 2 plus a half. Okay. Then we can get an expression for c to the power of 1 from the psi 1 stationary state. So Griffiths did this one actually. So he got m omega over pi h bar to the 1/4 times square root 2m omega over h bar times x e to the minus m omega over 2h bar x squared, which we'll simplify as alpha times root 2 times c e to the minus c squared over 2. And from that, we'll get a form of c as just psi 1 over alpha root 2 times e to the positive c squared over 2. Okay. Let's plug those into our time-independent state first, and then do the last thing. So we've got alpha over 5, 1 minus 4 psi 1 over alpha root 2 e to the c squared over 2 plus 4 psi 2 over alpha root 2 e to the positive c squared over 2 plus 4 over 2 times e to the minus c squared over 2. And then that simplifies. 1 plus 2 is 3. We've got 2 times root 2 psi 1 over alpha e to the positive c squared over 2 plus 2 root 2 psi 2 over alpha e to the c squared over 2, and then all times this thing on the side. So as silly as it sounds, now we can look at the stationary state psi 0 and use it to get an expression for c to the 0, which is 1, which we'll plug in right there. So psi 0, according to Griffiths, is m omega over pi h bar to the 1/4 e to the minus m omega over 2h bar x squared, or in our notation, alpha e to the minus c squared over 2. And so it looks like 1 is equal to psi 0 over alpha times e to the positive c squared over 2. So we're going to use that to write this. It's alpha over 5, 3 psi 0 over alpha e to the positive e to the positive c squared over 2 minus 2 root 2 psi 1 over alpha e to the c squared over 2 plus 2 root 2 psi 2 over alpha e to the positive c squared over 2 e to the minus c squared over 2. And now we can let all these alphas go away and all of the exponents go away. So we just have 3 over 5 psi 0 minus 2 root 2 psi 1, and that's over 5, plus 2 root 2 over 5 psi 2. And so, mission accomplished, we've written it as the stationary states, which means we have a few constants defined now. So C0 for this is 3/5. C1 is minus 2 root 2 over 5. C2 is 2 root 2 over 5 as well. And so obviously the energy values that we could observe are E0, E1, and E2, where the energy eigenvalues for the harmonic oscillator are just n plus a half times h bar omega. So we can observe E0, which is h bar omega over 2, with a probability of the square of C0, so it's 9/25. We could observe E1, which is 3 h bar omega over 2, with a probability of the square of C1, which is 8/25. And then we can observe E2, which is 5 h bar omega over 2, with the probability, oh my god, the probability of C2 squared, which is 8/25 as well. And those all add up to 1, so that's pretty cool. Finally, the expectation value of the energy, H, will be E0P0 plus E1P1 plus E2P2. So it's h bar omega over 2 times 9/25 plus 3 h bar omega over 2 times 8/25 plus 5 h bar omega over 2 times 8/25. So we got h bar omega over 50, and then we have 9 plus 3 times 8 is 24, 5 times 8 is 40. And I think that is 73. Yeah. So you add those numbers up, you get 73 h bar omega over 50. Not the nicest number in the world, but it's right. So throw grossness to the wind, I guess. The last thing that the problem asks is, let's say that after a time capital T, the wave function looks like this. B is some constant plus 2 square root m omega over h bar x all squared e to the minus m omega x squared over 2h bar, which in our notation is b times 1 plus 2c squared e to the minus c squared over 2. And we'll expand it so it's b1 plus 4c, oh my god, 4c plus 4c squared e to the minus c squared over 2. So also we know that we can expand this and turn it into the stationary states like we did before, and the constants are the same. So we can go ahead and say that this is b over 5, 3 psi 0 plus 2 root 2 psi 1 plus 2 root 2 psi 2, right? So that's kind of crazy. What we need to do is we need to take our result for the initial wave function, and I'm going to steal it from up here. And then we know that the time-dependent version of that is just going to be attaching some time propagation pieces to each. So this is going to be e to the I e1 t over h bar. And let me actually write capital T instead of little t. Minus 2 root 2 over 5 e to the minus I e2 capital T over h bar plus 2 root 2 over 5e to the minus I e3 capital T over h bar. And we know what those energy values are, so let's just write them out. We got e to the minus I omega capital T over 2 minus 2 root 2 over 5 e to the minus I, and it's actually minus 3 I omega t over 2 plus 2 root 2 over 5 e to the minus 5 I omega t over 2. Right. So I'm going to factor out some stuff. We're going to factor out a factor of 5 and also e to the minus I omega capital T over 2 here. And so we'll have just 3 psi 0 minus 2 root 2 times e, and then 3 halves minus 1 half is 1. So just minus I omega t plus 2 root 2 psi 2. I realize now that I've been dropping some psi's. There's supposed to be a psi 1 here and a psi 2 here. I guess I got a little bit fast and loose. Let's just do it like this. Psi 1 plus 2, and then the time piece, so e to the minus I omega t plus 2 root 2 psi 2 e to the minus, and then it's 2 I omega t. Right. And then, so it looks like this expression here is also like almost matching this expression here. There's just a difference of a minus sign on this second term and a plus sign on the second term up here. So for this to work, it looks like b equals e to the minus I omega t over 2. And e to the minus I omega capital T has to be equal to minus 1 for this to be true. And so minus 1 just represents a half cycle, and then the lowest half cycle is just pi. So it looks like t equals pi over omega. Okay.